Let's talk about factoring, not just how to factor, do it. You'll see this in quadratics and polynomial functions all the time. The key step when solving equations, finding zeros, and simplifying expressions. So today we're going to go over really quick factoring quadratics and polynomials, the factor theorem and its applications with synthetic division. It helps us solve equations like f of x equals 0. So if this is f of x equals 0, we are setting the function f of x equal to 0. We're not setting x equal to 0. This is going to be our 0. And we're going to be able to use factoring to help us rewrite functions in a more useful form. We factor when the expression is set equal to 0 or when we want to understand the shape or behavior of a graph. We can understand the shape or behavior of a graph by finding the zeros and allowing that to help us plot the graph. So here in example 1, we're going to be factoring x squared plus 5x plus 6. So the question that we want to ask is, taking 6, what multiples of 6 add to 5? Or that is, what factors add to 6 to get to 5? Take a second to think about that. So the multiples of 6 that add to 5 are going to be 2 and 3, right? The other multiples of 6 are 1 and 6, but that won't add to 5. Our answer is going to be x plus 2 times x plus 3. Always set it up in the way where you have your parentheses, then you have your x values, because when you have a quadratic, this is always going to be the setup. The zeros are what? Setting each of these to 0, we get x equals -2 and x equals -3 when we solve them algebraically. In example number 2, we're going to factor x cubed minus x minus 6x. Let's find the greatest common factor in this cubic function. The only common factor here is going to be x. We're just going to take out that x. We're going to make it x times x squared minus x minus 6, which further factors to x times x minus 3 times x plus 2. So if you can find a greatest common factor and do quadratic factoring, you're going to be in good shape. So our zeros, our solution here is going to be x equals 0 and x equals 4. Pulling from this being 0 and this being x equals 4. Let's take a quick look at the factors theorem. So the factors theorem states that if f of c, so an f of any constant, equals 0, then x minus c is a factor. So if we had something like x minus 4, right, where c is 4, that equals 0, so x equals 4. If we had x plus 8 equals 0, so that would mean x minus 8 is the 0. We're adding 4 to both sides, and we get x equals 4. We're subtracting 8. Cancel that out from both sides, and we get x equals -8. All right, so for our fourth example here, we're going to start out with the factor theorem. We're going to move into synthetic division. All right, let's get into it. So f of x equals x cubed minus 6x squared plus 11x minus 6. So right here, we're going to just try something. We're going to try to get a 0 or a factor just by happenstance, right? Let's start with the easiest one that we can start with. Let's do c, or that constant, in the equation of c equals 0, where x minus c is a factor, right? We're going to say c is 1, so that x minus 1 is a factor. We're going to plug in c here, right? Going back here, f of c equals 0, right? Where we're plugging c in as a value of x. So f of 1 is going to equal, plug this in, 1 cubed, that's 1, minus 6 times x, or times 1 squared, so that's minus 6, plus 11 times 1, that's just 11, and then minus 6. We take this and we solve it, we're going to get 0. 1 plus 11 is 12, so they cancel out to equal 0. So therefore, x minus 1 is a factor. We're going to use synthetic division to divide f of x by x minus 1. So how can we take this big, scary cubic polynomial function and divide it by x minus 1? That's what synthetic division is here for, right? So here's the setup for synthetic division. We use the 0 as a divisor. Okay, so the 0, x minus 1, this is x equals 1. So then we set that up as the divisor. And then we use coefficients from the original equation. So the original equation here is x cubed minus 6x squared plus 11x minus 6. So we're going to use the coefficients and the constant from the original equation. So this is 1 minus 6 plus 11 minus 6. So first of all, we just write out those coefficients in the first row here. 1 minus 6 plus 11 minus 6. All right. And then I'm going to carry down that 1 every time, right? Whatever number is here, whatever that leading coefficient is, I'm just going to carry it down. Then the way synthetic division works is it just treats each of these values that we're going to add in this step. So you can almost treat this area, remembering back to long division, as the quotient area, because this is going to give us the coefficients of our next equation that x minus 1 will multiply by to get to f of x in this statement. So that's what we're trying to get to by seeing, all right, what does this factor multiply to get to this original equation? So we carry down the 1, and then what we're going to do is we're just going to take this 1, we're going to multiply it by our divisor. That's going to give us 1, and then we'll add negative 6 plus 1, which is like 6 minus 1, which is 5. And we're going to add that to 11. So 11 minus 5 really is what we have here is 6. And then again, we're going to take the divisor. We're going to multiply it by that remainder here. We're going to get 6, positive 6 here. And then negative 6 plus positive 6, neither one of them is greater. So they cancel each other out and we get 0. Now our coefficients, we're going to take these coefficients, 1, negative 5, and 6. 0 is x'd out. If this wasn't 0, that means that an x minus 1 is not a factor. So these pieces are basically our quotient of the synthetic division. It's just set up a little bit differently from the way we used to do long division. So we're going to take those coefficients from the synthetic division, that is 1, negative 5, and positive 6, and we're going to create a quadratic equation, right? So now we have that original factor that we plugged in to our synthetic division, and we got out our coefficients that now we can create this quadratic, and that factor multiplies by the quadratic to give us our original function, that original cubic polynomial. And then we factor this quadratic once more, we get x minus 2 and x minus 3. So our zeros are going to be x equals 1, x equals 2, and x is. So to wrap up, factoring is your tool to unlock solutions and understand function behavior by finding the zeros. So use the factor theorem to test possible roots. Then synthetic division to reduce the polynomial. It's clean, efficient, and powerful. All right, let's clean up your integer operations. Groups of operators that we're going to use when we're doing integer operations. That's addition and subtraction are in their own kind of little family, and then multiplication and division are in their own separate family, right? They abide by different rules. Within each, though, we're going to have same sign or different sign that's respective to the rules within addition or subtraction, or multiplication and division. So addition and subtraction, the rule is when we have the same sign, we add and keep the sign. So negative 3 plus negative 5, same sign. We're just going to add them like normal. Okay, 3 plus 5, that's 8. And then a negative 8. That's it. Add and subtracting different signs. The rule is we're going to subtract. Whether we're adding or subtracting, we're just going to subtract. And we will keep the sign of the bigger valued number. So here we have 10 minus 14. That's negative 4. Okay. 10 minus 14 is the same thing as 10 plus negative 14. So let's take a quick look at multiplication and division. Same sign. The rule is same sign, it's positive. Done. If we have 3 numbers, it's a little different. Just take them 2 at a time. So negative 4 times negative 3 equals 12. Positive. 4 times 3 also equals 12. The rule is that different signs equal negative, right? So again, we pair these in 2s. So this rule applies. So negative 7 times 2 is negative 14. Here's a quick combo example. First, what we're going to do is what's in the parentheses here, order of operation, PEMDAS. 4 minus 6 is going to be negative 2 plus negative 3 times negative 2. Then we'll do multiplication, which is negative 2 times negative 2, same sign. So it's going to be positive. So this will be 6. And then our final answer is 10. So today we're going to look at leading coefficients, what they tell you about the graph. So what does the leading coefficient do to the graph? Let's take a look. So the leading coefficient is equal to the number in front of the highest degree term, right? So if we have 3x to the 4th power, and this is the highest degree term, the 3 is the leading coefficient. And what the leading coefficient does is it controls the direction and the steepness of the graph. Just the slope of a linear function would control the steepness of a graph. So we're going to go over polynomials one by one, starting with quadratics. So starting with quadratics, we have x squared, which is going to open up, right? It's a positive value, that parabola. Negative x squared is going to open down. When we have a whole number, that leading coefficient, we're going to have a narrower graph, right? So narrower graph, larger y-intercept. It's going to take longer for it to cross that y-intercept. We have a narrower graph. With 1/2 x squared, we're actually going to have a wider function. So if this is our parent function, then our graph might look something like that, right? Cubic functions, when we have x cubed, it's going to be the standard S curve, okay? 2 turning points here. Okay, that's positive x cubed. Negative x cubed would be something like this in the third quadrant, negative. 2x squared, it's going to be, it's steeper, it's a larger y-intercept, and 1/2 x cubed is going to be flatter. So it's going to be, this was the x-axis, it would be something more like that, rather than something more like for the standard x cubed S curve. So the quadratic function, it's going to be a flat bottom u, right? That can shift into a w, okay, depending on if it's positive with x-intercepts or negative with x-intercepts. It'll look more like an m. But it's going to be a flat bottom u in the parent function, right? For 5x to the 4th power, it's going to be very steep, and for 1/4, it's going to be a wider u. So to wrap up, the leading coefficient controls the shape, direction, and scale of the graph. Think of its attitude, A for leading coefficient. Let's talk about vertical and horizontal asymptotes, what they are and how to find them. Asymptotes are invisible boundaries. They come in 2 varieties, the vertical and the horizontal asymptotes. Vertical asymptotes are going to be the set. So in order to find the vertical asymptote, we're going to set the entire denominator, that is the function or that lone term, equal to 0. So when f of x equals 1 over x minus 2, we take that x minus 2 and we set it equal to 0, and then solve it algebraically. Vertical asymptote is x equals 2. Horizontal asymptote. So we compare the degrees of the numerator and the denominator to get the horizontal asymptote. Now, the rules here are a little more complex for the horizontal asymptote. So when the degree of the numerator is greater than the denominator, we have none. We have no horizontal asymptote. This is not the same thing as y equals 0. None is the correct answer there. When the degrees of the numerator equal the degrees of the denominator, we're going to have y equal to the ratio of the leading coefficients. And we'll go through some examples in a moment. The third option here is when we have the degrees of the numerator are less than the degrees of the denominator, y is equal to 0. So when we have f of x equals 3x squared plus 5 over 2x squared minus 1, the degrees of the numerator are equal to the degrees of the denominator. So then, according to our rules, we look at, oh, here's number 2, great. So we take the coefficient ratio, which is 3 over 2 of the leading coefficients, 3 over 2, and the y then equals 3/2. So here's our next example, f of x equals x over the quantity x squared plus 1. So the degree of the numerator is less than the degree of the denominator. Okay, so this degree of x is less than x squared. Therefore, y equals 0 according to our third rule here. Finally, we have f of x equals 3x to the fourth power minus 5 over the quantity 2x squared plus 10 greater than the denominator. Therefore, we have none, according to rule number 1 here. So just a quick wrap up. The vertical asymptote is where the graph is undefined, right? It's some function over 0. And then the horizontal asymptote is where the graph levels off. So when it's coming down to the x-axis and it levels off before the x-axis. So today we're going to go over exponent rules. So here's exponent rules, the 5 you need to know. Rule number 1, the product of powers rule. Okay, this is a big one. Same base. Okay, so the x value here and the exponent is the same. You just add the exponents. So the exponents here are 3 and 4. We add them together, we get x to the 7th power. Rule 2, power of a power rule, so multiplication of exponents. So this is when we have a power inside of parentheses, and then we have another power we're taking on the outside. We just multiply the exponents. So 2 and 3 equals x to the 6th power. Rule number 3 is the quotient of powers. So we have the same base, x here. We subtract the exponents. So x to the 5th power over x to the 2nd power equals x to the 5th minus 2, which equals x to the 3rd. We flip that and do a separate problem, x to the 2nd power divided by x to the 5th power. We get x to the 2 minus 5, which is x to the negative 3rd, which is 1 over x to the 3rd power. Rule number 4 is the zero exponent rule. So any non-zero base to the 0th power equals 1. So 5 to the 0 power equals 1, x to the 0 power equals 1, y to the 0 power equals 1, 10 to the 0 power equals 1. 1,000 to the 0 power equals 1. Rule number 5, last one, is the negative exponent rule. Now, this refers back to what we talked about just a moment ago with the quotient rule, and this is related to that last example. So what we do when we have an exponent to the negative power, we're going to flip the base to make the exponent positive. So x to the negative 2, it's going to be 1 over x squared. 1 over x to the negative 3rd power is actually going to be x to the 3rd power, because we just flip it back to the numerator, and we have a positive exponent. So remember, same base, we're going to combine the exponents. Whether it's the product of a power of a product rule, or the power of a quotient rule. The power of a power will be combining the exponents through multiplication. So a little word to the wise, watch out for negative powers and parentheses. Keep these 5 rules sharp and everything else gets easier.